Good afternoon. Um, Welcome to the Smith River Nuisance Algae Study online public meeting. Um, Got a few housekeeping things to discuss quickly before we start. The presentation is being streamed live and recorded. If you have questions or comments that you would like to have addressed at the end of the presentation, you can type those into the YouTube chat comments section. My apologies for being a little bit stuffed up. I'm not sick. I just have some allergy problems. So with that, we will get started again. This is the Smith River Nuisance Algae Study and Beneficial Use Assessment Update. And I am Chase Bell, the project manager of this study, and I will give you a status update from the data we have collected from 2018 and 2019 field seasons. To start off, some special thanks to the FWP folks and the Smith River State Park. We couldn't have collected the amount of data within the float reach that we did without them, so shout out to those guys. And special thanks to our field help this past summer, as well as our student intern and other various DEQ staff that assisted in data collection and equipment support as well. So what prompted this project? In 2015, DEQ and FWP started to receive reports of nuisance algae growth on the Smith River, and that continued through 2017. And in 2018, we initiated the ongoing project, Smith River Nuisance Algae Study. A historic timeline for some preliminary data collection that was done in 2016. FWP sampled a few sites for nutrients, specifically nitrogen and phosphorus, in 2016, and then DEQ sampled 9 sites on the main stem of the Smith River and 2 tributaries in 2017, and then in 2018 we began the ongoing study we'll talk about now in this presentation, that we're going into our final year, our 3rd year of sampling in 2020. So why is this project important? The Smith River is a quite valuable recreation stream for the state of Montana. It's a permitted float stream as well. You have to draw a permit to float it. And excess algae growth can inhibit the quality of recreation experience that one might have on the Smith River. Another reason that this is important is aquatic life concerns, mostly with taxa or bugs. There could be a shift river-wide of bug communities, that being, for example, a caddisfly or mayfly system might move over time into more of a scud bug community if these algae growth events persist over time. We also could potentially see low dissolved oxygen impacts in our shoreline areas and back eddies. And that could have an adverse effect on juvenile fish. But we don't expect to see a large impact of dissolved oxygen within the main stem of the river because it is high gradient and has quite significant flow to keep those dissolved oxygen levels up. Some key terms that we'll discuss, these are used throughout the presentation today. First being Cladophora glomerata, which is the identified algae reaching nuisance levels in the Smith River. It is not a harmful algae to humans and is also native to Montana. Nutrients for this project is directly in reference to nitrogen and phosphorus concentrations in the water column. So anytime we reference nutrients, that's what we're talking about. Our p-value is a statistical measure for confidence. So if we state that there's a p-value, for example, a p-value of 0.1, that means we're 90% confident and 90% certain the trend we are seeing in the data is really occurring. And I'll explain the p-values a little bit more when we're in the slides that relate to p-values and statistical analysis as well. Our growing season, we talk about a growing season, that's when numeric nutrient standards are applicable. It's where we'll most likely to see adverse effects to aquatic life as well, and that time frame is July 1st through September 30th. Water year as well is capturing the rise, fall, and base flow of the hydrograph, which is October 1st to September 30th. So we developed this overarching question in the winter of 2018, why is Cladophora reaching nuisance levels in the Smith River and why now? And we developed some potential causal variables from literature and other research that has been done and kind of honed in on these presented here. Regional microclimate changes, so that's air temperature and white sulfur. Our water temperature in the Smith River, discharge patterns, hydrology and scour, nutrients, so nitrogen and phosphorus concentrations in the Smith River, nutrient limitation. We'll discuss nutrient limitation in depth later. Basically, in short, it is what nutrient, nitrogen or phosphorus or both, is not sufficiently available for algal uptake in the river, and the timing of tributary contributions. So what is their contribution of nutrients and what is the timing of those tributary contributions. And then phosphorus, or excuse me, pH. pH is a known parameter that Cladophora has an ideal growing condition that is above 7, and all of the data we have collected from 2017 to 2019 has shown that the pH is above 7, so that's an ideal growing condition for the Smith River. We have ruled out that a change in pH is causing this to get back at that why now question. Water hardness. Water hardness is also a parameter that we know is a driver. If the conditions are right, Cladophora likes a certain condition, and that milligrams, 121 milligrams of calcium carbonate is anything above that, Cladophora tends to like best and can grow rapidly when other conditions are right. In 2018, our minimum recorded value was 141 milligrams per liter of calcium carbonate, and then in 2019 we had a sample in early May that was 114, so that's a little bit below our minimum threshold, but by the time other conditions within the river came into play to create a good situation for algae growth, those concentrations were back up above 121 milligrams per liter. So that's another parameter that we don't think is causing algae growth now. It's been that way. We have data from the 70s and 90s that has similar values to what we're seeing now. So we don't think that's a driving factor to answer the why now question. So to give kind of a spatial representation and scope of this project, we sampled from the headwaters to the mouth, and these are our monitoring locations. We sampled roughly 25 main stem sites and 10 tributaries from headwaters to mouth, and that's represented with the M next to the number or the T. And our float reach, we reference the recreation float reach, which is from Camp Baker to Eden Bridge. And that in this map is outlined by the red bars. So kind of think about this as we think about this spatial representation as we move through this presentation. So we'll start getting into data here, kind of moving forward throughout the presentation. Specifically in terms of our runoff time frame and discharge for a couple gauges in the Smith River and then some weather data. We look at trends over time, and we use the Kendall family of tests, which is non-parametric. It was developed by the USGS. It's widely used for trend analysis in environmental sciences. And we use a statistical significance threshold of 0.1, and we'll present our p-values in the graphs as well. So what we looked at in terms of runoff was magnitude and timing, and what is the magnitude of our yearly peak flow? So how much flow each year are we seeing? Also, what is the timing of those flows? So what is the center of mass timing? And what that means is on what day of the water year does 50% of the flow for that water year pass a single point? In this case, it's a gauge just downstream of Camp Baker. What is our time to peak spring flows? And what is our duration of those peak flows? So we look at the lag time in days of the water year from when 50% of the volume for 1 year to 75% of the volume for 1 year passes a single point. We also use some correlations, one of them being the Spearman and Rank correlation, which we have a graph showing flow versus temperature, and that as well uses a p-value of 0.1. For our data analysis, we chose a time frame of May 15th to July 1st. And the reason we did that is this is when the Smith River is usually floatable. So recreation floating is most abundant during this time. We also capture the rise and fall of the hydrograph, so we capture that spring runoff time frame back into sometimes into lower base flows. We also see water temperature rise to cladophora preference during this time, and we'll get more into what that cladophora preference is. And literature that we have reviewed also indicates that this is when air temperatures are trending warmer. So we'll look at air temperature first. This is a air temperature from White Sulphur Springs, Montana weather station. And that right-hand graph shows all of the years and weeks within that May 1st or May 15th to July 1st time frame. It's kind of just a gauge to present all of the data and show that trend that's moving warmer over time from 1997 to 2019. And if you focus in on week 23 on the right-hand side, the right graph, that's kind of a middle ground representation of all of the data that we have collected and analyzed. And what we're seeing from this temperature data, what's presented here is our minimum daily air temperatures. And we're seeing that those are significantly increasing over the entire May 15th to July 1st time period with a statistical or a p-value of 0.02 on the seasonal Kendall test. And that equates to a 3.3 degree Fahrenheit increase over the 23-year period of record that we have and analyzed. Now moving into water temperature, this is representing the same thing, May 15th through July 1st. We can see here that some weeks are warming and others are not. And our temperature increases in June are occurring beyond the effect of flow. So the green band in the right-hand figure shows the temperature preference for Cladophora. That's the algae we're studying in this stream. And as you can see in that right-hand graph, over time, the water temperatures are slowly increasing to be closer and closer to that minimum threshold for Cladophora growth. So for April, May, June, and July, the only month that is significantly warming with a p-value of 0.09 is our month of June. And water temperature is significantly increasing during the first 2 weeks of June at a p-value of 0.04. So what we're looking at is in June, we're 96%, roughly 96% certain that these trends are actually occurring. Into some relationship between water temperature and flow. This is looking at May. We have discharge on the left-hand side, and down on the bottom we have water temperature in degrees Fahrenheit. The red line across the bottom of the graph at 250 cubic feet per second is the minimum recommended float guidance for rafts for the Smith River. So we use that as a baseline metric to understand when algae would be observed or not based on floaters, recreation floaters, and who or how many people might be on the river. What this graph shows is the month of May in all years that we have water temperature on record. The month of May is usually too cold. But as you can see on that arrow at the top, as we move towards the 52 degrees Fahrenheit and move towards the warmer side of things, that arrow gets green, which moves us into the month of June. This is the same graph in the way that it's presented. We have flow, our average monthly flow on the left-hand side from 0 to 2,500. And then we have our water temperature in degrees Fahrenheit down at the bottom. The green box is for the preference of Cladophora growth. It's when Cladophora grows the best. It might grow at limited rates below about 55.4 degrees, but we know it likes anything above that. So kind of to walk through this graph a little bit, in 1997, we see a high discharge, which is outside of that green box. And we can rule that out as a year, even though water temperatures were warm enough to support algae growth, water was likely too high, there was too much flow, and there was too much turbidity in the water, so you couldn't see to the bottom. Likely didn't see reports through there for that year. In 02, 13, and 99, we looked at that, those June average temperatures fall within the in the water temperature range for Cladophora growth. But what we saw is in the data 2000, those 3 years specifically had the first half of June was too cold to support Cladophora growth. So that might be an explanation of why we didn't receive reports during that time. In 2000 and 2001, we used that 250 CFS or 200 flow of 250 to kind of explain why we might not have heard reports during those 2 years, 2000 and 2001. There probably wasn't a lot of floaters, recreation floaters on the river during that time. Into 2015, 16, 17, 18, and 19, all of those years are within the Cladophora water temperature range. They had discharge or flow values that were low enough to support clarity in the stream so we could see down to the bottom and observe algae growth. And in those years, we have observed algae growth. We have 3 question mark years that we can't really explain. There's no obvious reasons why we didn't see or hear of reports of algae growth. They're an unknown at this point for why we haven't seen those. With few exceptions, the first half of June was in the optimal range, 55.4 to 63 degrees, and flows were not too high in the most recent year since 2015. Moving on to runoff patterns, we look at runoff patterns from USGS gauges in the upper part of the river, which is just below the start of the float reach near Camp Baker. That has a period of record from 97 to 2018. We have some provisional data for 2019 and decided that it needed to be corrected before we use it in our data analysis. The other gauge that ends in 500 is at the end of the float reach upstream of Hound Creek. So the end of the float reach, and we have some historical record from 1951 to 69, and then it picks up again 2006 to 2019. What we saw from those 2 gauges is there's no significant trends over time for either magnitude or timing of flow at either gauge. And for the upper gauge, we have no significant trend for the duration of the peak flow. What the literature suggests is that we have missed that change in timing, or that occurred during the mid-1980s. Our data sets would have missed that since we have the 50s and 60s, and then not again until the late 90s. So we had missed that. More on hydrology. In 2018, we had a near record discharge. It was the 3rd highest peak flow on record, and it presented the project with a natural experiment. Even though we had fairly high flows, near record flows, we still saw algae growth in the middle of June in the lower river. As you can see in the photo right there, that's a June 17th photo. And then as you can see on the graph down at the bottom, that 2018 discharge was the 3rd highest on record. Because of that, we're not certain that discharge or hydrology effects are affecting the growth of algae and overwintering filaments as much as we had originally thought. We do have data to produce a model if we think that it's necessary when we have some more, if we have some more question marks. Into algae growth itself, Mike Saplee did a study that looked at how green is too green, the opinion of what constitutes nuisance algae levels. And that's why we use nuisance algae in this presentation, and why we use that term, as well as to differentiate between a harmful algal bloom. What you can see in this figure is a clear stream to a 60% cover stream. And that middle picture is about where public started to say that this was a nuisance, which is about 30% cover, 120 milligrams per square meter in that photo. Just a little bit above that is where the public's opinion said that it was a nuisance for recreation. In that the two photos on the far right is July 2018 on the Smith River near the end of the canyon. And it's very similar to what we see on that bottom right picture of 60% cover in the Clark Fork River. So these algae growth events are reaching nuisance levels. And to better characterize that, we have some methods to assess algal biomass visually as we float the Smith River to get a better understanding of what the algae conditions are throughout the float reach. In 2018 and 2019, our floats, we used a systematic visual assessment roughly every 2 river miles. And when we saw tributary effects or where the algae pattern changed, whether increased or decreased downstream of a tributary, we took additional visual assessments to better characterize those. And what we found through that is this figure you see here. 2018 is the blue line, 2019 float is the orange line. Camp Baker, this shows the float reach, so mile 0 is Camp Baker all the way to Eden Bridge, which is the takeout. And what we see here is the upper river above Deep Creek is lower than the lower river, and it's also variable. This could be due to groundwater influences or just river conditions, river velocity, substrate types. If it has the perfect conditions within the river, that's where we see the variability. Both years we didn't see a drastic increase or decrease where tenderfoot comes in, but moving into the Deep Creek area, we did both years see a big jump of algae growth in percent cover downstream of Deep Creek. We also saw that, because we saw that in 18, we decided to try to better understand the influence of flow that Deep Creek has. And when we floated it in late June to early July, we calculated with some flow measurements that a little under 300 CFS, or cubic feet per second, of flow is coming in from the Deep Creek drainage. This is a wilderness area. There's very little human land use. It's a pretty pristine area. And of that 300 CFS, only about 30 CFS is from surface water. So that's a large influx of groundwater coming in from that tributary. And then moving into where Hound Creek comes in, we see the opposite of what happens in Deep Creek, or where Deep Creek comes in. Both years, 2 years in a row, we saw a significant decrease of algae growth downstream of Hound Creek. The unmixed area where Hound Creek comes in shows a solid line of where the unmixed water is, where the Smith River water is full of algae, about 80% cover, and where it is coming out of Hound Creek, there's no algae or very little filamentous algae, Cladophora. So that gives us a picture of what the growth patterns are throughout the float reach. Now moving into more water chemistry stuff, our nutrient concentrations, nitrogen and phosphorus. We looked at the current data that we have collected, 2017, 18, and 19, versus the historical data that we have from the 1970s and 1990s. We also look at the patterns of nutrient concentrations in space and time from 2018 and 2019 to see if there's similarities or difference between the 2 years. We also deployed nutrient diffusing substrates. I'll explain those in depth when we get to that part of the presentation, but an overview, those substrates we deploy in the river for roughly 22 days, 2 times during the summer at 5 locations, and those diffusing substrates give us a better understanding of what nutrient, nitrogen or phosphorus, or both, is not sufficiently available for algae to uptake and grow. We also take Cladophora tissue and send those in for analysis, and those analyses are for carbon, nitrogen, and phosphorus, and we can relate that to the nutrient diffusing substrates to better understand what our limiting nutrient is. So our nitrate plus nitrite historical data versus our current data. The top graph is for the growing season, so July 1st to September 30th. We have milligrams per liter on the left-hand side, and then we have the sites ordered from upstream to downstream from left to right. The blue bars are the historical data, the orange bars are our current data from 2017 to 2019, and what we see is our nitrate concentrations, both during the growing season and non-growing season, are generally below what the historical data shows. During the growing season, we could have some algae uptake, which might be reducing those nutrients. We have a far more robust data set for our current data than we do in our historical data. But generally what we see is we're a little bit lower now than we were historically. This total phosphorus comparison is set up the same way. So our blue bars are historical data, and our orange bars are current data. During the growing season, we are a little bit higher than we were historically, but not significantly. Our error bars that we have there still overlap. We're kind of right in line with where we were at in the 1970s and 1990s. And then during the non-growing season as well, it's similar. We're right in line. No significant change over time. Then for our current data, so this looks at 2018 and 2019 total nitrogen data. So we have kind of walked through this figure a little bit. The top figure is 2018, bottom figure is 2019. They are scaled the same. Milligrams per liter is on the left-hand side going up from 0 to 1.1 milligrams per liter on both figures. And each of those boxes with different colors represent a sampling trip over the field season. So in 2018, we started in April and concluded in October. 2019, we started in May and concluded in October. Generally, what we see here is what is typical of western Montana streams, mountainous streams. We usually see higher nutrient concentrations, total nitrogen for this figure, earlier in the season. This is the runoff period, more volume, more suspended sediment. 2018 and 2019 are a little bit different in terms of nutrient concentrations in the early season, which is likely explained by the weather that we had late in the season. So we had a rainy spring in 2018, lots of discharge or flow in the Smith River, and it kind of followed that typical high to low pattern that we see. But in 2019, we were really cold. We were still froze up. We might have been capturing more of a baseline condition with some lowland runoff. Whereas in early May and late May and then into mid-June, we see that variability in nutrient concentrations, which probably aligns with some runoff and rain events that happen. As we move later into the season, the bars on there are the numeric nutrient standards. And what we see is we generally fall below the numeric standards. And this kind of aligns with our algae growth pattern that we see in early July to late June to early July. We see that nutrient concentrations are a little bit higher. We're seeing algae growth is also higher during that time. And when we move into later into the summer, when those nutrient concentrations fall below the numeric standard, our algae growth also slows and we don't see as much growth within the float reach. Moving to our total phosphorus data, it shows a similar pattern as total nitrogen. This is the same figure and how it's laid out. 2018 on top, 2019 on the bottom, milligrams per liter on the left-hand side, and then each box represents a trip during the field season, starting in 2018 in April through October, and 2019 May through October. We see a similar pattern in this total phosphorus data that we see in total nitrogen. We're higher in the springtime during the runoff flows, typical of western Montana, mountainous stream systems, and then as we move into the growing season, that late June, early July to the end of September, the concentrations of total phosphorus are largely below the numeric standards. There's breaks in those standard bars due to ecoregions that the Smith River flows through. So each ecoregion within the Smith River corridor has a slightly different numeric standard. Moving to our dissolved orthophosphate or soluble reactive phosphorus, it's also called SRP. The unusual part of this is almost always during the field season when we're out sampling, we see phosphorus, dissolved orthophosphates at detectable levels. That's an unusual characteristic of these western Montana or mountainous streams. And we're investigating that more through this project as well to try to better understand why that is. Is it soils, geology, land use? Try to get a better understanding of why we're seeing almost always detectable levels of orthophosphate. Now into nutrient limitation. Nutrient limitation is an indication of which nutrient is not sufficiently available in the water for the algae to use to grow. So what a nutrient diffusing rack is we add nutrients to those vials to see which one is limiting. So kind of walk through the figure there. We have a control group which doesn't have any nutrient addition to it. We have a nitrogen group which we add nitrogen to the agar or jelly-like substance that's in those vials. A phosphorus group which we add phosphorus to the agar, and then nitrogen and phosphorus together to see what is not available, sufficiently available in the water for algae to use. And in this photo, you can kind of see the nitrogen and phosphorus addition group has a little bit darker color, more of a green color to it. That is a visual indication that nitrogen and phosphorus is co-limiting in this stream. This was a late deployment in late August to September. So what do those nutrient diffusing substrates tell us in terms of what's going on in the Smith River over a season? It follows similar to what we see in the algae pattern. Is early season when there's more nutrients available. Our nutrient diffusers in July largely reflect that all 5 sites that we deployed at largely reflect that figure on the left-hand side. It is never limited by phosphorus, so phosphorus is always available. In the early season in July, the Smith River is slightly limited by nitrogen or slightly co-limited by nitrogen and phosphorus. The reason it's not significant is because of those error bars and the overlap that they have with each other. Our nitrogen or our carbon, nitrogen, and phosphorus tissue analysis that we did of Cladophora in July that was taken on our float trip indicated a similar thing. In the upper river, algae was not strongly limited by nitrogen or phosphorus, but in the lower river, the algae analysis showed more of a nitrogen limitation. But as we move to later into the summer, August into September, 2018 and 2019 were similar in what the patterns show. We see a nitrogen and phosphorus co-limitation. So what that's saying is, later in the summer, nitrogen and phosphorus are both at low enough concentrations to not support robust algae growth. And we have also observed that in our sampling events. And that the difference of those two events is shown in those figures, where the right-hand figure is the August to September deployment. Because we see phosphorus, dissolved phosphorus specifically at detectable levels throughout the field season, we decided to move forward with sampling for phosphorus in a more in-depth way and looking at the tributaries and what their influence on phosphorus concentration is in the Smith River at Camp Baker. And what we found through that is we looked at bioavailable phosphorus. So bioavailable phosphorus is soluble phosphorus dissolved in water plus phosphorus that can readily desorb from suspended sediments. So during those runoff time frames in June is what this figure shows. That suspended sediment plus what's already dissolved in the water column plus the flow of those streams gives us a total bioavailable phosphorus contribution. And what we're seeing is about 25 and 17% of the total load calculated at Camp Baker. So we measure discharge or flow in all of these tributaries, take the water samples and calculate a load to that, and relate that percentage to what the total load is at Camp Baker. The North Fork of the Smith River and Camas Creek showed the most percentage of bioavailable phosphorus or phosphorus loading in relation to that gauge or the site at Camp Baker. In 2020, we have partnered with USGS to take a better, closer look at this to better understand the timing. So we'll have real-time gauge, stream gauge data, so we'll know what the real-time flow is. We'll know what the real-time turbidity, so how murky the water is. We'll have real-time turbidity data, and then we'll also have an automated sampler that can take water samples in increments when we can't be there, because we can't be there on site all the time. So it'll take those samples and we'll have a better, higher resolution data set to extrapolate out to other tributaries as well, and hopefully get a better picture of when these tributaries are contributing what in terms of phosphorus load and how that relates to the Smith River in their total contribution. So we'll start from the beginning again, kind of a recap of our findings as of today, March 18th. Over the past 23 years, from late spring to early summer, our local air temperature has increased 3.3 degrees. Smith River water temperature has also significantly increased. Specifically, the first half of June is significantly warmer. We're kind of refining that and getting a better understanding of our June time frame and how that relates to algae growth. And then our runoff patterns, there has been no significant changes in runoff over the 23 years of record in magnitude, duration, or timing. For Smith River water temperature, to kind of recap that, May is too cold to support growth. June is often optimal for cladophor growth during the lower flow years in terms of water temperature. And then 2015 through 2019, they were all conducive to algae growth, and we saw the water temperatures were conducive to algae growth, and we saw nuisance growth. We observed that. In other Junes conducive to growth, 2003, 2007, and 2006, we don't know of a growth event, and the reasons for that are unclear. The Smith River is kind of a perfect place for algae to grow with its substrate and velocity and the morphology of it. So to continue on some recap of findings, Smith River nutrient concentrations, so nitrogen and phosphorus. Historical nutrient concentrations are not notably different than today. If anything, our nitrate concentrations appear to be lower than the past. Again, that's a low or a small or smaller sample size of data, but that's generally what we see. If anything, it's lower than in the past decades. Today, our concentrations are high enough in spring and early summer for algae growth. Nutrient concentrations mostly fall below numeric limits later in the summer. We'll look more into ways to reduce those even further if we can to limit algae growth and try to get a better handle on algae growth in the late spring, early summer time frame. For nutrient limitation, June and July, algae is not limited by nutrients, nitrogen or phosphorus, maybe slightly limited by nitrogen or slightly limited by both nitrogen and phosphorus. In August of 2019, nitrogen and phosphorus limitation was most common through the floatable reach. So nitrogen and phosphorus concentrations were too low to support robust algae growth. Sources of bioavailable phosphorus in 2019, we found Some tributaries are substantial sources of phosphorus during the June runoff time frame. We are exploring in 2020 whether better control could help address nuisance algae, especially in June. More detailed study of this, like I said, is planned with partnership with USGS for the 2020 field season. We've ruled out kind of the scouring of algae by spring runoff. It doesn't seem to be an important factor because of that natural experiment that happened in 2018 with a near record flow event. So what are our conclusions as of today? For cladophora growth specifically, June appears to be undergoing change. Water temperatures during June are often warm enough to support rapid growth and trending warmer. The first half of June might be our important time frame to commence this cladophora growth. June 2018 and 2019 nutrient concentrations are also high enough to support cladophora growth, and orthophosphate is abundant. Later in the summer, those nutrient concentrations, nitrogen and phosphorus, usually develop into a co-limitation that probably limits the cladophora growth. So back to that first question, why is cladophora reaching nuisance levels in the Smith River and why now? Of those causal variables that we were looking at throughout this project, we see that air temperature changes over time and water temperature changes over time are our kind of main points that we're looking at and we'll continue to look at. Discharge patterns and timing, magnitude, and duration, as well as hydrology and scour. We don't see those as changing over time or being a significant player in answering the why now question. We do have record to look at recent changes in nutrient concentrations, pH, water hardness. They're all playing a role in algae growth, but from the historical data that we do have, we haven't seen a significant change over time. That might be to a limited data set or those changes aren't actually occurring. So moving forward, we're still looking at air temperature and water temperature, relating all these parameters and causal variables together to try to develop a strategy to build resiliency in the Smith River for algae growth in the future. So our future predictions, looking at the 2020 field season, June will likely manifest nuisance growth going forward. Water temperatures are favorable. Water temperatures and air temperatures are trending warmer. And the first half of June, like I said before, is an important, it may be important as a growth trigger. 2018 and 2019 data showed nutrients are generally sufficiently available to support algae growth, and the potential to reduce phosphorus to sufficiently low levels in June to affect cladophora growth is being investigated further in 2020 and hopefully give us a better picture of what steps we can take to reduce those concentrations. So for our 2020 monitoring and sampling strategy, it's going to be very similar to what we did in 2019. We're going to characterize current conditions from upstream to downstream, so headwaters to mouth. We will look at the timing of algae growth, when that occurs in the field season. We'll focus in on tributaries that we've identified in 2018 and 2019, where phosphorus loads in 2019 were highest in June, and then in 2018 and 2019, where changing Smith River algal patterns were observed. We will continue the trend analysis, deploy nutrient diffusing substrates again, and continue to compare our current data to historical data. That is all I have. We will look at questions now, if we have questions.
So far.
Can type those questions into the chat if you have questions you would like us to address. My contact information is on there as well. If you have further questions that we don't address today, feel free to send me an email and we will get back to you with an answer to those questions. All right, it doesn't look like we are getting any questions from you guys. Again, use my contact information if you do have questions that you would like addressed. We will get back to you and address those questions via email. Thank you for attending, and again, any questions, feel free to contact me at any time.